All right, here we go. This is the first video on the unit for the universe. Um, you can pause this video anytime you need to take a look at anything you need to. The learning goals, I'm not sure how I'm going to assess these yet, but here they are. I want you to be able to explain Hubble's law, explain how we know the universe is expanding, discuss the rate of expansion, that's like how fast it is actually expanding, and discuss the distribution of galaxies and voids in our universe. Basically, how does our universe look like, or what does it look like? So, the fact that our universe is expanding, um, it's one of the most important, uh, you know, discoveries that we've ever made in astronomy. And one of the people who kind of got this started was Slipher. You may recognize this name from one of your CLAs. So it it seems kind of silly, but it began with the search for Martians and other solar systems. So in 1894, a controversial astronomer, Percival Lowell, established an observatory in Flagstaff, Arizona, and he wanted to study the planets and search for life in the universe. And Lowell thought that the spiral nebula, it might be other solar systems in the process of forming. Again, 1894. This is before we realized what a galaxy was and that there were other galaxies. And he asked one of his young astronomers, Vesto Slipher, to photograph the spectra of some of these spiral nebula. Again, we didn't know they were galaxies. To see if they were, if their chemical composition might look like something that we might expect from newly forming planets. So the scope that was being used was a 24-inch refractor telescope. It was not suited to look at faint spiraling nebula. Remember, our atmosphere and the glass in these refractors kind of bends and distorts the light. So with the technology of that day, photographic plates had to be exposed for 20 to 40 hours just to produce a good spectrum. And that meant continuing the exposure of the same photograph over several nights. So beginning in 1912, over a period of 20 years, Slipher photographed the spectra of more than 40 nebula. That's what we call dedication. It took a lot of effort to do this. So what Slipher found, though, is that the spectral lines of most galaxies, at this point, I think we're starting to figure out they were galaxies, showed a very large redshift. That meant that source of light was moving away. And Slipher's observations showed that most spirals were just racing away at velocities up to 1,800 kilometers per second. That's fast. A few spirals, such as the Andromeda, some other things in the local group, they're approaching us, so there's a blue shift, but all the other galaxies were moving away. Slipher announced his discovery in 1914, years before Hubble showed that these objects were, in fact, other galaxies, and before anyone knew exactly how far away they were. No one at the time knew what to do with that discovery. So, the implications of Slipher's work, it became very apparent during the 1920s. Georgios Lemurier, I can't pronounce that. He was a Belgian-born priest and a trained astronomer. In 1927, he published a paper in a very obscure Belgian journal. Translates to a homogeneous universe of constant mass and growing radius, accounting for the radial velocity of extragalactic nebula. Quite a lot there. And what this priest discovered was that Einstein's equations for relativity, which we discussed before, were consistent with an expanding universe. He then went on to use Slipher's data to support the hypothesis that the universe is actually expanding, and he was able to estimate a rate for that. So by the late 1920s, Hubble and Milton Humas, using Mount Wilson's 2.5 meter telescope, improve the accuracy of measuring the distances to these spiral galaxies, and they were able to measure much fainter, more distant galaxies than Slipher could. So when Hubble laid his own distance estimates next to the measurements of recession velocities, he found a relationship between distances and velocities for galaxies. And this is where it gets a little crazy. And this is something that's kind of important here. So let me highlight this. Um, what he found was that um, the farther away a galaxy is, the faster it's moving. That's not very intuitive, but the farther away a galaxy is, the faster it's moving. So in 1931, Hubble and Humason jointly published a paper where they compared distances and velocities of remote galaxies and found speeds as high as 20,000 kilometers per second. And they were able to show that the recession velocities of these galaxies are directly proportional to their distance. Just as I can't pronounce his name, as the priest had suggested here. So we see a graph here, and we see a slope. That means it's predictable. So in other words, if we can measure velocity, we can now measure distance. So this gives us a way of measuring distances in outer space. And we now know that this relationship holds true for every galaxy, except for a very few of the nearest ones. So nearly all of the galaxies that are approaching us are part of the Milky Way's local group. So again, that's the Andromeda, Triangulum, a few others. So when we write this down as a formula, we get this formula right here for velocity. Velocity equals capital H times d, where capital H is a number called the Hubble's constant, d is distance, and v is speed. And it just comes from this graph right here. You can think of y equals mx plus b, y being the velocity, m being the slope, x being distance. So y equals mx and then plus 0. So really, if we have a really, really good number for Hubble's constant, we have a way of calculating speeds. So it all comes down to Hubble's constant. How good can we measure that? So astronomers, they use some crazy units, and for us, for Hubble's constant, we're going to be using this unit primarily, kilometers per second per million light years. So for several years, estimates for the value of Hubble's constant have been a range of 15 to 30 kilometers per second per million light year. And if we kind of take the median, if we assume a 22 for this, that means a galaxy moves away from us at a speed of 22 kilometers per second for every million light years. So if we've got a galaxy that is 100 million light years away, it's going to be moving at 2,200 kilometers per second. And Hubble's law then, it tells us something very fundamental about the universe. Since all except for the nearest galaxies appear to be moving away from us, the most distant ones are moving the fastest. That means that we must be living in an expanding universe. And this is very important. Our universe is expanding. It's getting bigger and bigger. Now, we get a built-in bonus here. Always love bonuses here. Hubble's constant also gives us a way of calculating distances. And if we first reliably establish Hubble's constant by measuring both the distance and velocity of many closer galaxies, in many directions, we need to be sure that Hubble's law is truly universal. But once we've calculated a value for that, and we're satisfied that it applies everywhere, we can basically use this to calculate distance. So a little bit of math here. If we find a galaxy that's moving at 18,000 kilometers per second, and we can do that using spectra, redshifts. Using a Hubble constant of 22, we can take our formula, we can rearrange it for distance. Distance is v over Hubble's constant. We can calculate that galaxy must be 818 million light years away. So using Hubble's law, we can measure distances in outer space. And that's a really, really good thing, because astronomy, the most important thing is measuring distances. So the use of redshift is a very important technique for determining distances. The use of Hubble's law as a distance indicator requires only the spectrum of a galaxy. Because remember, that spectrum gives us the speed. We can take a look at how the spectra is shifted, red shifted or blue shifted, and that gives us the velocity. So with larger telescopes, more modern spectrographs, spectra can be taken from very, very faint galaxies. But this is important. The technique works if and only if the Hubble constant is truly constant. Okay, that's very important there. So before 1998, astronomers thought that although the universe is expanding, the expansion would slow down because gravity pulls. So they thought, okay, the universe got started, it's expanding, and then it's starting to slow down in its expansion. And so if the expansion is slowing down, then Hubble's constant should be decreasing over time. Well, that might not be the case. Maybe it is. So when we take a look at Type 1a supernova, so remember that's the white dwarf one, we use those as standard bulbs, and it gives astronomers the tools they need to observe extremely distant galaxies and measure the rate of expansion billions of years ago. And the results were very unexpected. It turns out that the expansion of the universe is actually accelerating with time. That's not expected. So a decelerating, a slowing down of the universe would be explained by gravity. There's no force or property in the universe that we know of that could account for acceleration. For my physics students, remember that net force causes acceleration. If there's an acceleration, there must be a force that causes that acceleration. So where is it? What is the force pushing the universe apart? If Hubble's constant is not a constant, then the calculations of galactic distances is not accurate. So later we'll talk about this in more detail, but for now, Hubble's law gives us a good estimate for the expanding universe. Okay, so for some of the models here, then, are all galaxies really moving away from us? Is there something special about our position in the universe? These are important questions here. And the fact that galaxies are moving away from us and that more distant ones are doing it faster shows that the universe is expanding uniformly. And a uniformly expanding universe is one that is expanding at the same rate everywhere. So in that kind of universe, we and all other observers, no matter where we are located, must observe a proportionality between the velocities and distances of equally remote galaxies. So imagine a ruler, and we make this ruler out of rubber, and we put our lines for the centimeters, and someone starts stretching that ruler so it doubles in its length for every minute. And we're going to take some intelligent ants. So this part's important, and we put them at the 2, 4, 7, and 12 mark. And then we begin stretching this ruler. And let's say we are on the 2 centimeter mark. So the ant that was at the 4 centimeter mark was originally 2 centimeters from us. That has doubled its distance in 1 minute. So that means it is moved away at a speed of 2 centimeters per second. The ant that was at the 7 was originally 5 centimeters from us. It is now 10 centimeters away, so it has to have moved at 5 centimeters per minute. And the ant that was at 12, originally 10 centimeters from us, is now 20 centimeters away. So it had to be moving at 10 centimeters per minute. So if we take a look at this, what we see is that the ant that is farther away is moving faster than the ant that was originally closer. And again, that's if we are the ant at 2 centimeters. Well, that doesn't make a whole lot of sense, especially when we realize that the ruler itself is expanding at a constant rate. So these ants at different distances are moving at different speeds, and their speed is proportional to their linear distance, and that's Hubble's law. If we repeat the analysis but make our intelligent ant on some other mark, let's say the 7 centimeter mark, we discover that as long as the ruler stretches uniformly, that ant also finds every other ant moving away at speeds proportional to their distance. So in this analogy here, the ants represent galaxies, and the ruler represents space, or as Einstein would put it, space-time. So as space-time is stretching, the galaxies which are embedded in it are moving farther apart from each other. So this relationship expressed by Hubble's law can be explained by a uniform stretching of the world of the ants. So for us, this world would be space-time, the stuff that galaxies are stuck to. And all of the ants in our diagram will see the other ants moving away as that ruler stretches. All right, I think that's a good place to stop for this first video. Stay tuned for the second video.